Hello everyone, welcome back. This is Engineer Hussein Mwasapi, and in this video we'll be looking at how to find the angle between a given vector, preferably a force vector, and a segment, as well as the projection of the given vector along the particular segment. So we're trying to find the angle in between a given vector and the segment. Not just that, as well as finding the projection of the given vector along the particular segment. So before we begin, do not forget to like and subscribe to the channel. Alright, so to easily understand this, we're going to use the concept of the example that I'm going to solve for you. So in this example, we'll understand clearly how you can find that particular angle in between a given vector and the segment, as long as the projection along that particular segment. So the question says that the pipe in the figure is subjected to a force which is 100 pounds. Determine the angle, which is theta, between the force and the pipe segment BA. So you have the force, which is 80 pounds there, and the pipe segment is here. As well as determining the projection of F along this segment. Alright, so for you to easily understand this, you need to know that this force will have its own projections. But I'll talk about projections later. Let's first determine the angle in between the force and the pipe segment. So we're looking for this angle, theta. It's in between the force which is 80 pounds, and the pipe segment, which is from B to A. The force, 80 pounds, is from B to C. So now to determine the angle in between F and the segment, we first have to establish the position vectors. Since the angle that we're looking for is at B, which means it's angle CBA, or others could write it as ABC. So I'm trying to look for the positions from B to C, then B to A, or rather B to A or B to C. Either ways, it will still come out. So I'll start by first looking for the position vectors of BC and BA. So let us find these position vectors. Now that we know what we need to find, let us find the position vectors separately. Alright, so I'll create my own data and look for the position of RBA. Now for RBA, you need to understand that RBA is B to A. So this is B to A. And if it's B to A, it implies that this will be A minus what? B. So let's find the positions at A as well as B. So let's start with the position at A. The position at A is simply acting along one point using this point as our reference, because that's the origin. That's where the X, Y, and Z is coming out from. So this means that this is our origin. You can just let it, or assume that it's O. Therefore, from the origin to the point where A is acting along the y-axis only. So which means that we're only going to have a position along the y-axis. Therefore, it has no position in the x, so that's 0 in the I, and it has one position in the j, which is in the y, so plus 1 in the j, and it has no position in the z, so I'll say plus 0 in the k. By now, I hope we are familiar with how to collect the points or the positions of a given point. Alright, so for B is here. So now, from the reference, we need to know how to get to B. So now, how are we going to get to B? How are we going to do that? So we can get to B by moving first in the x, then y and z, because it's I, j, k. So let's first move in the x. So in the x, for me to reach b, I need to move in that direction. When I move in that direction, I reach that point. And that direction means that I'm moving 2 feet in the x-axis. So I have 2 in the I. After that, I need to move from that point to another point where I'll find b. So I'll move along the y-axis like that. And this will give me, I'm having 1 foot there plus 2 feet there, which means I'm going to have 3 feet. So plus 3 feet in the what? J. Once I find those feet, I need now to go to B. To go to B, I'm going to go downwards. Now going downwards simply means that I'm moving in the z-axis and I'm moving in the negative z-axis because simply I'm going downwards. So I'm going to have a minus in the k. I'm going to have -1 in the k-axis. Alright, now that I've established the points that I need, I can now find the position vector of what I need. So the position vector over, is somewhere here, of RBA is equal to A minus B. And this will be as follows. So I write the positions of A, which is 0, 1, and 0, and the positions of B, which is 2, 3, and -1. Remember, this is in the I, this is in the J, and this is particularly in the K. After that, I'll just do my algebra. 0 minus 2, that would be -2. 1 minus 3, that's -2. 0 minus -1, it's a +1. This implies that the position of RBA is equivalent to -2 in the I, -2 in the J, +1 in the K. So that is our position vector for RBA. Now that we have our position vector, we can as well find the magnitude, which is the length of this particular line. So let's find the magnitude of the position. To find the magnitude, we'll square the components that are in the I, J, and K, and then take their root. So we have -2 squared plus -2 squared plus 1 squared. This will give us the root of 9, giving us 3. Now all these positions are in feet, so this would be in feet, as well as this would be in what? Feet. Now in a similar manner as we have done for RBA, let's do the same for RBC. So I'll get the information that we have now for RBA and put it somewhere so I can store it somewhere. Alright, so I'm erasing this. So now let me put it here as our data 1. So RBA has been found to have the positions -2 in the I, -2 in the J, +1 in the K. And these are in feet. Not just that, its magnitude, which is RBA, has been found to be 3 feet. Now, after doing this, let us now do the same for RBC. So I'm going to erase what we have, getting my magic eraser. Alright, getting back my pen. So, for those of you who feel like you can attempt to do or find RBC, you can always pause the video and attempt to do it on your own. Then continue with me. Alright, so this simply means that we're now going to find data 2. And data 2 talks about the position vector of RBC. This simply means that you're looking for C minus what? B. So C minus B is simply because I'm moving from B going to C. Hope that's clear. So let's find the positions at C and the positions at what? B. So to find the positions at B were already found. We found the position at B to be 2 in the I, plus 3 in the J, minus 1 in the K. I hope you can recall. Then we can now find the positions at C. Now to find the position at C, I want you to look closely. Now from the origin, which is O, C is acting only in the X there, which implies that we'll only have one position, and that position will be in the X. Any point that acts along either the X, Y, or Z will only have one position, and that position will be its position in that particular axis. For instance, we're having point C in the X alone, which means that we're only going to have its position in the X, which simply means we have 2 in the I, and the rest to be nothing, which is 0 in the J, plus 0 in the what? K. Upon having this information, you can now compute C minus B. C minus B simply means we get the C values, which is 2, 0, and 0, then the B values, which is 2, 3, and minus 1. We know this is in the I, this is in the J, and this is particularly in the K. If we do our algebra, we'll have 2 minus 2, which will be 0, 0 minus 3, which is minus 3, and then we'll have 0 minus minus 1, which will give me a plus 1. Therefore, my position of our BC will be equivalent to 0 in the I, minus 3 in the J, plus 1 in the K. So this is my position vector of BC. So I can now find the length or the magnitude of this same position. So RBC, remember to root all the components, to square all the components and then root their answer. So this will be 0 squared plus minus 3 squared plus 1 squared, which will give us the root of 10. So I'm just going to leave it as a root of 10 because I don't want to end up having decimals. But if you want, you can always get the decimal fraction, round off to a certain number of significant figures, then use it. Alright, so remember, these are in fits, so we say fits, then this side we say fits. Yeah. Alright, so now that we have that information, we can also put it somewhere. So I'll say, I'm now having my RBC, and my RBC is 0 in the I, minus 3 in the J, plus 1 in the K. And I'm having my magnitude of RBC to be equivalent to the root of what? 10. And all these are fits. Fits. Alright, now, why were we doing this? Let me erase this. Alright. Now, be mindful of this. We were finding the positions simply because to find the angle, which is, sorry about that, let me get my pen back. To find the angle, which is cos theta, it is always equivalent to the dot product of RBA dotted with RBC over the product of their magnitudes. Like that. Therefore, with that in mind, we can say cos theta is equal to the dot product of RBA, which is minus 2 in the I, minus 2 in the J, plus 1 in the K, dotted with RBC, which is 0 in the I, minus 3 in the J, plus 1 in the K, over the magnitude of RBA, which is 3, times the magnitude of RBC, which is root 10. Now remember, when it comes to the dot product, it's always you multiplying the component in the I with that in the I. So minus 2, so just show it. So that would be minus 2 times 0 plus minus 2 times negative 3 plus 1 times 1 over 3 times root 10. Therefore, cos theta is equal to, if we compute this, we'll have 7 over 3 root 10. Now to find theta, you need to understand that theta will be equivalent to cos inverse of 7 over 3 root 10. Therefore, theta will be equivalent to, if we punch this, we'll have 42.45015554 degrees. If I round off to 2 decimal places, as usual, I'll have 42.45 degrees. And this is the angle in between the two vectors. Now that we have the angle, we can find the projection of the given force. Now, how are we going to find the projection of the given force? How are we going to find the projection of the given force? Alright, so I need you to understand something. We're looking for the projection of the force. The projection will have, this force will have the projection that will be parallel and perpendicular to it. So you have the perpendicular component here. I'll draw it just like that. And then the parallel component like that. So since the angle is acting in between in between BC and BA, you need to find the projection along BA. But if the angle is acting in between BC and another point, let's say B something, would have found the projection which is perpendicular at that point. I hope it's clear. So now, since it's, let me just show it something like this. Since we're having the 80 there, the 80 pounds, this is B, this is BC, then we have BA, and then the angle is here, theta. We're going to find the projection along this point. Sorry, we're going to find the projection along this point because the angle is acting in between this and that point. But if the angle is here, rather, would have found the projection along this point, which is the perpendicular projection. So we're trying to look for this projection, which is BA. Now, if I draw this in a way that you can see, so you have this. For those of you who watch the video on how to find the projections that are parallel and perpendicular, you will recall from what I explained in this. But if you didn't, you can always go back and check for the video and watch. So this is theta, and this is the 90 degrees. This is the 80. This is B, C, and that's A. So if we label our shapes, we have the hypotenuse of the opposite and the adjacent. So we know that we're going to use the trig ratios because it's a right angle triangle, which is the famous SOHCAHTOA. So now, given one side and an angle which we found to be 42.45, in order for you to find the side you're interested in, always concentrate on the side given and the side you're being asked to find. So the side given is the hype, and the side you want to find is the adjacent. So the trig ratio having that is CA. So we're going to use CA. CA is equivalent to cos theta is equal to adjacent over the hype. Therefore, if we cross multiply, we have the adjacent being equal to cos theta times the hype. Now, simply because the adjacent is the force we want to find, which is force BA. Therefore, force BA will be equivalent to cos theta, of which the angle is 42.45, times the hypotenuse, and the hypotenuse is the force F, which is 80 pounds. So if we compute this, force BA will be equivalent to 59.02932957. Rounding off to 2 decimal places, force BA is equivalent to 59.03. These are going to be in pounds. So this is the magnitude of the projection of the force along the segment BA. I hope it's clear. So this is how you go about solving for the angle in between a force and a segment and the projection along that particular segment. Alright, thanks for watching. Remember, slow progress is better than no progress. And if you have any queries, you can always reach me on WhatsApp on the line 077 149 5252. Remember to strategize before you become a statistic. Let's try and push for that A+.